Okay, so we are now ready for our next talk. So that is by Suvodip Mukherjee, again from TIFR. And he will tell us about studying primordial black holes using gravitational wave observations. Suvodip, please.
Very much, and thanks for the organizers for inviting me to give this talk. So in the beginning of the part today, we have heard search for dark matter from LHC. Now we'll change the gear a bit, coming to one more ground-based experiment, like LIGO, Virgo, Kagra. And what we can learn from it about, not so much about dark matter, but about to focus on this primordial part of the primordial black hole. So what I will try to convince you that the existence of primordial black holes can be explored directly from observations of LIGO, Virgo, Kagra, and in future from other ground-based and space-based gravitational wave detectors, and which can be open up a completely discovery space or will rule out primordial black holes scenario. So in this setup, I think this plot in its different avatars has been already shown. I just want to make the point here that with the help of several electromagnetic observations, we are able to understand or map the cosmic history, what the universe is possibly has gone through. Some of the facts, some of the things we have learned are really observation driven, such as cosmic microwave background radiation has proven what is back there at a redshift of around 1100. We have signatures of cosmic reionization, again through several observations. And in the very low redshift, we have detected millions of galaxies, their stellar properties. So, and also at very low redshifts, we have measured supernovas and so on. So this has really helped us in bridging what I call as bridging between different redshifts to understand the history of the universe. Some things which you have learned from this picture is that, well, stars were not there in the universe forever. Stars formed are typically in very low redshift, if I want to compare that with the cosmic microwave background radiation redshift. So there is a kind of history which is concurrent in our mind that, okay, most of the stars in the universe you have seen are mostly in the low redshift. I will show you some plots on that. And we'll argue at how this the simple fact can turn out to be a very neat window to actually explore the primordial nature of primordial black holes. So in this frontier, what's I keep on talking in every talk I give is the real sector which is opening up very neat data-driven way is basically gravitational waves and electromagnetic waves observations. The multi-messenger domain of cosmology and astrophysics, really thanks to several ongoing or upcoming electromagnetic observations spanning way from radio to gamma ray. I have seen in the schedule that there are several talks on electromagnetic probes of cosmology already. I will not be speaking time on that. What I'll be covering is the other sector, which is now being slowly coming up as an observational probe to us, the gravitational wave probes, which similar to electromagnetic observations turns out to be also something which is multi-band. And in this, we can see gravitational wave signatures from extremely high frequency signal to a very low frequency. So in the left-hand side of this plot, you are seeing signals which are currently detectable from the ground-based detectors, such as LIGO, Virgo, Kagra. In future, from LIGO India, Cosmic Explorer, Einstein Telescope. These are the sources which are particularly, you can detect masses of around few tens to hundreds of solar mass, up to quite higher shift. So this is the plot you are seeing, up to which we can detect gravitational wave sources as an individual event. So in blue, you are seeing in advanced LIGO, the take-home message is a total solar mass of around 100, we can detect up to a redshift of 1.5. Okay, which is great. That means these are cosmological sources. You can actually go up to high redshift to understand the cosmic properties, precisely the way we are doing so far with observations from EM sector, like like supernovas, galaxies, quasars, and so on. And in future, this domain will be expanded to the help of Cosmic Explorer in magenta and Einstein telescope in green, up to quite a high redshift and 70, 80 in the similar mass range of a few solar mass to few tens to thousands of solar mass. Okay. Then comes the range, which is one can explore from millihertz gravitational wave signal using space-based detector like LISA, which we can explore up to around redshift of 20. Again, remember the previous plot which I was showing you. These are again pretty much cosmological distances. So these are cosmological probes of sources of few thousands to millions solar masses. So now the inspiraling black holes, which are driven by a single law of gravity, hopefully that is correct, Einstein theory of general relativity, that will tell us what's happening over here, and that will also tell us what is happening over here and at all other bands. So that means I have a very new and neat probe, astrophysical probe, which I can use to study cosmology. Story is also very similar in other bands, like at the or even lower frequency gravitational wave signals, like nanohertz gravitational waves emitted from billion solar mass systems, 9 solar mass objects, which you can detect using Pulsar timing array. I will not talk about this at all, or my today's talk is not directly quite relevant, so I'll not focus much on this. And the other sector is, of course, the we want to measure the gravitational signal at the largest wavelength, at the smallest frequency, which is possible only by cosmic microwave background radiation through B-mode polarization. So that's my spectrum about which we are going to measure it. But the question now we can ask that what are we going to learn from this process? Why are they so special about? What are they really going to bring up to us? And one thing I would like to tell you, again, I think I promote a bit more nowadays on this sector, that the real thing which gravitational wave is able to bring to us, if I need to put that into a simple picture, I will say that we can explain the gravitational wave observations very nicely on this 4-dimensional plot where is a length, redshift, source, and time scale. These 4 sectors, which makes really a gravitational wave source very unique probe to explore cosmology or astrophysics. These sources, as I already told you, if you see the length part, you can basically explore physics from kilometer scales, where the 2 binary objects are very nearby and coalescing, a few kilometer size. Its physics is driven by galactic scales physics, which is in parsec, kiloparsec scales. And they are all explored in cosmological distances, which I'll be coming up soon. So they are basically seeing length scales over these huge scales by a single kind of source. And that is really unique for 2 gravitational sources. Secondly, these sources are explored from up to very high redshift. As I already told you, right now our horizon is somewhere up over here, but we'll be soon going up to high redshift with the help of LISA, Cosmic Explorer, and Einstein telescope. These sources varies with time. They are transients by very nature. Some of the sources will be of order of a few milliseconds, and some of the sources you can be seeing for years. A same source of different masses and driven by the same laws of physics will be possibly can tell you a lot about fundamental physics thing if you can really monitor and model the temporal behavior of such signals. And finally, there are many kinds of sources. You have binary neutron star black hole, binary black holes, intermediate mass black holes, extreme Banerjee spirals, and supermassive black holes. And these all sources are going to be very useful. And what I would like to really admire is that gravitational sector can really span very nicely these 4 sector domains. And this opens up, with the help of these specific features of gravitational wave observation, what we really can start opening up with the help of ground-based, space-based detectors about both fundamental physics aspects and different science cases, spanning from strong gravity tests to multi-messenger cosmology. And if you're interested in phase-time singularities, phase-time phase transitions, to astroparticle physics. So these last few blocks are what is mostly interested in the group over here, but it depends upon what is your research interest. You will possibly find something or the other in this bucket. of multi-messenger science. This is a review article written by us as a part of STOMAS Decadal. So you can please take a look into it. And why it is really possible to thanks to the funding agencies for funding LVK and in future LIGO India, A+, Next Generation Gravitational Reactor, which is still not funded, and LISA, which is funded and hopefully will be flying by 2036. Today, I'll be talking particularly about a single sector on these several science cases which one can explore, which is about probing primordial black holes using gravitational waves.
IISER is fully funded. All
Yeah.
three are-
NASA IISER has was pushing it for a while. Now NASA has already joined it. It's happening. Sorry, I'm a bit unwell because of a flu, but I'm better today. So sorry if I'm crashing my voice a bit. All right. So, so I think I lost my voice. Okay, so let's try to focus on this astrophysical and the primordial plot of the black hole. If we detect a pair of black holes from LIGO detectors, let's for time being, this is my schematic diagram of showing you two black holes. Is it, if I ask you a question, is it an astrophysical black hole or a primordial black hole? What will you really characterize about it? There are several windows by which I can produce black holes of different masses. So it's really not a super clean window unless it's really false, you know, like where astrophysical black holes are totally unexpected. If so, it's great. So possibly the mass and the redshift plane is a nice place to distinguish between astrophysical black holes and primordial black holes. So what about astrophysical black holes? By very definition, what is astrophysical black holes? The astrophysical black holes are black holes which are formed from the death of stars. So they should be tracing the stellar properties, right? So we know, I was trying to argue in the very beginning from our simple picture of a universe which we have understood so far. From multiple electromagnetic observations, we have kind of mapped the, thank you so much. Thank you so much. Thank you. Okay, so from the electromagnetic observations, what we have really mapped, though the error bars are large, but you can still see it's not that uncertain to really get a peak in the star formation rate in the universe. In simple word, many of you already know that there is this noon in the cosmic noon when the stars were forming the most, which is around a shift of 2. And there's a sharp decline at higher redshift and so at a lower redshift. So the binary coalescence which you see today in LIGO observations, the individual events, those will be forming from these stars, and depending upon their formational channels, they will also trace the similar star formation rate, as I'm showing over here in this plot. These are for different formational channels, which is basically delays their delay time of a star to form and a black hole to merge. It's a delay time distribution. We don't need it too much in these talks. I'll not focus much on that. But what is the main take-home message from this plot is if the black holes are of astrophysical nature, they will follow the astrophysical star formation. And they will be also following the astrophysical mass distributions of the stars. Yeah.
Is it possible that that delay,
that
itself becomes redshift dependent
Yes.
in non-trivial way?
Uh-huh.
Can you wash out the
Yes, you can.
information?
You can make it very bad anything this side. So your time delay is always a positive number. So you can, once the star form, you can be completely redshift dependent and get this feature very different. But you cannot form a black hole before the stars has formed. So that means your time delay can never be negative. It's always positive quantity. So depending upon at what look back time you are observing, universe will spend a finite amount of time, and that can be redshift dependent for different formation channels. But you will still, if you go to significantly higher redshift, this decline in the property is unique. Yes, it's too low.
Points go up and down.
Yeah, if this point goes, you will only care about the shape of the curve, not the normalization. It comes soon to that. And as far as the rate of star formation at high redshift is decreasing, we are in a good shape. Totally, it is true. I'll show you how this astrophysical and primordial black holes distinguishes. So, and there where the signature come from, precisely. Yeah, please go ahead. Yeah, please go on, yeah. Precisely, yeah, that's the whole point I'm giving this talk today. Right, I'll show up a table soon on that. Thank you.
Oh, also
Yeah.
the IMF can be Z dependent. And the IMF, what actually does is
The mass distribution. Yes, the initial mass function of
that
the
can have a redshift.
yes,
We don't know.
which you do not know. So that's the whole reason when someone wants to get an understanding about a black hole you have seen as an event, that's what he was mentioning, and want to argue it is an astrophysical nature or primordial, which is a very risky game. That's precisely the reason. One of the reason is IMF uncertainties. Other reason I already mentioned is the reason because of the
No, but even that shape.
this shape, you mean?
If you go back.
This shape, yeah. This is
The right hand shape. The N
Uh-huh.
waves versus Z.
uh-huh.
Right? He's mentioned that you can have a redshift modulation.
Yes.
One cause of the redshift modulation could be the unknown IMF. So it's not just the star formation that's unknown.
Yes.
The IMF is also unknown.
It is. So let us put levels of our ignorance. Our level.
Before that, can you
Yeah.
explain what is IMF?
Initial mass function. So we do not know what is the initial distribution of stars in the universe. We have a model for it. They say initial Cooper mass function or saltpeter mass function. There are several mass functions. They're all theoretical models. We want to constrain them. We have some limits on that. But our current, we have a huge amount of ignorance on that. But the level of ignorance on the black hole formation channels is way larger than our ignorance in the stellar properties. We have seen some stars. At least at the like lower end, we have some distribution which agrees with some observations. Black hole formation channels is a larger number, it's a much bigger uncertainty which is currently there, which you do not know. That's the physics which you would like to infer from observations.
Black hole formation or black hole merger?
Black hole merge, so formation channels by which black holes can merge. That which decides the delay time distribution. Are they forming in a cluster? Or are they forming, like in a much shallower region? Are they forming from hierarchical mergers, or are they actually in a binary? These all are the huge amount of uncertainties where you really want to go from event to event to understand about the properties. But precisely that's the point, is that there is a huge amount of astrophysical uncertainty which will kick in if you really want to understand about astrophysical black holes with great details to make sure that whatever you are detecting is definitely a primordial nature. I think that important part is whether it's a primordial or not, that's what we want to follow. Yeah. Yes, I have a chart on that. I'll come out in very soon. Just stay with me. Just stay with me. Another thing is mass. That's what you are saying. Below 2 is like a mass gap. There is a lower end of the mass gap. Below 2, we do not expect it to be black hole at all. Or there is a higher mass gap, which is basically coming from the paired instability supernovas. So this is a plot by Robert Farmer. In the y-axis, you are seeing the black hole masses which can form from a star. In the x-axis, you are seeing the core mass of the star. What is interesting is that as you keep on increasing the core mass, you still keep on forming black holes of higher masses. But after a certain mass, you do not form any more black holes. They try to die off. So you do not have black holes above a certain range, even though you have core mass quite high. This is called the maximum mass because of the paired instability supernova. What it means is that when the black holes on the stars are very large, you can have oscillations in the stars. And that can really disrupt the star completely, ending up having no black hole at all. So, or in other simple way, extremely large, heavy star may not end up having a black hole at all because of throwing away all its material through it. Okay. This is not a very new physics. This is known for 20 years. If you go back to history, it's a completely theory paradigm. Hence, Bethe, Dick Bond did the calculations analytically. Then people started using simulations, and now people are using sophisticated simulations to explore what are the real boundaries we have on the pair instability supernova masses. But I have to say that again, these are a very simple astrophysical simulations. They're like really 1D stellar model. Stars are not 1D, as you all know. Yeah. Yes. Masses, yeah. 45 to 60, depending upon metallicity, depending upon prescription of the winds, depending upon nuclear rates, and so on. Yeah, that's a completely different talk. I can.
So there's a gap, and then you have these supermasses.
That's right. That's right. Precisely. We have an evidence of this gap from LIGO data already. We can be very happy to chat about this. I was giving a talk on this in RRI meeting exactly a month back. So it's there. So that's, I'll show you a plot soon, but one of the way to what you were mentioning about the low mass, that's the region, lower mass gap, we put all of them as yellow stars. These are possibly our neutron stars. And if you go to higher mass end, you don't see individual black holes too many, except these two. I'll come back to it later. So this is that mass gap I'm talking about. There's one mass gap over here that you referred already, and the other is at the higher end. So astrophysical distributions, mass distributions are not going to be really continuous. They are going to be, they have some gaps. So when anyone will tell you, let us try to find black holes which are not astrophysical. The easiest way to go for those mass ranges is for those where there is no contamination from astrophysical. Those are the cleanest windows. That's over here, and that's over here. But unfortunately, if primordial black holes are rare, they are going to be so rare to be detected that it may not be sufficient for us in our given time, observation time limitation to really see significant of them or to rule out primordial black hole scenario or detect primordial black hole scenario. This one are the one which has combined to 2x2 events. So you combine 130, you get a 58 out of it. That's what's plotted over here. What we should see is any of these two are usually below 50. Under 50 solar mass, except these two, couple of them. So that's where people try to argue, are we seeing something of primordial nature or not? I have a better plot on this, but I need to at first tell you what we actually observe in LIGO data. Because ultimately we are doing something which is quite data driven, right? So what we really observe in LIGO data is the redshifted masses of the gravitational wave sources. Precisely because of expansion of the universe, as every observer probe we measure, their frequencies are redshifted. That leads, similarly, will be true for gravitational waves. And gravitational waves, because of that, the inferred masses we will be seeing will be also redshifted. That's precisely because there is no scale in the problem, mass scale in the general theory of relativity. So any mass you are seeing will be basically appearing like a redshift. Another thing which you very nicely measure in gravitational wave data is something what we call as the merger rate or number of sources I am measuring as a function of distance or redshift. That's another quantity we can measure quite nicely already from the current observations. There are other things like spin and so on, which also leads to some understanding about the astrophysical properties of these black holes. But we do not have yet a very neat measurement of the spin distribution so far. So now, if I want to tell you a single picture about what we have detected so far about gravitational wave sources, this is a plot by the LIGO-Virgo-Kagara collaboration telling us that so far around 90 sources which we have detected, What are the typical properties of their masses? This is O1, O2, and remaining are O3. O4 is starting in practically is about 2 months. Here, the way to read this plot is basically individual masses, M1, M2, and their total mass we have seen with the number, which the number index means their date and their time. But this may not be a very easy plot to understand, but maybe to answer your question, this is the plot which is made by one of my students, Aditya, trying to basically get this from empirical correlation. Take the LIGO data, just do an empirical correlations, and do we see a mass gap or not? And that's the place you should see. This is the plot of the primary masses detected. Take LIGO data, we measure distance, so there is no cosmology assumption going here. That's in the x-axis, and spin measure for the sources in color. What you can now start seeing at the low redshifts or less mercury distance, we do not have enough sources which are heavy. We should have seen this because this falls right in the center of our detector sensitivity. We should have seen them if they exist. So that means either they are rare or they are not happening quite a lot to us to detect. At higher redshift, there are a couple of them which are slightly high masses. These are the ones which are, like promising candidates for in the mass gap events. Similar story is for the secondary masses. By definition, secondary masses are those sources for which their mass M2 is less than M1. So it's no wonder why the y-axis have different range. But again, the story is quite similar that we have really kind of upper limit. Most sources exist up to some mass. Simple way. Of course, this is not the most sophisticated way to show a statistical plot.
These masses are redshift characters.
These are not. These are like real observations. This is actual masses time. Yes. These are so this no trimming of data. This is just you take the data and you show the correlation. We should have seen a lot of heavy mass objects anyway, and you don't see that at all. You can always, the thing which we are saying that is we have done in LIGO data, and there's also a paper with Christos and others where we have actually done a formal statistical analysis showing what is the statistical property of these black holes. And we have seen that there is an evidence of pair-inferior supernova masses. I will not have time to go on it today at all because I'm going to talk about primordial black holes. Yeah, please. You can convert this to redshift. So these will be around 0.8, 0.7, 0.8. So they are typically at high redshift. Coming down, yeah, that's right. That's right. So these will be actually somewhere here after to correct it, but still they are quite heavy. That's the issue. We have seen a few of them heavier sources, but we are not sure yet what is the real smoking gun signature.
Any model that could argue that
Yes.
these very high mass black holes may exist, but they may not exist in binary. Therefore, they're not their mergers, therefore not.
Yes, as I said, there are many models, and one of those possible astrophysical signatures are the uncertainties because of metallicity, nuclear rates. We can show that the uncertainty on the Roberts plot, Robert has himself made that plot, that there is some of this can be a 80-90 solar mass as well. It's not really something we can argue that it exists as non-astrophysical. But yeah, sure.
So there's also errors on the
Right, here there is no error bars just because I want to make this plot clean and neat, but I can share with you a plot which actually the full
Yeah, but the errors also increase with rate.
Correct. So these are more noisier than this.
Yeah, so those two high mass ones, one of them you can be certain.
Yeah. So here all of them are certain about, the error bars are quite large, but what is one of the take home you can really see that why there are so less events in this window where masses are heavy, so you should have detected them, the loud gravitational sources. And nearby, so their distances are small, they are really bright flux. Why am I not seeing them? Question is, so the basic question is this region. If black holes of very heavy solar mass exist, I should have seen them in this window. Exist quite a more in number in comparison to this, right? Everything is statistical. I have seen 90 events. I'm saying why none of the 90 events usually is over here and then over here. There's a trend. So when you compile the posterior distributions of the binary sources we have detected in LIGO, Virgo, Kagra, we indeed see at above 40, 45 solar mass, there is a steep decrease in the mass function of black holes. Today, unfortunately, I don't have plot on that. I can just take it, bring it up or during my discussion later. But stick with me that we have the full posterior measurement of this mass distribution as a function of mass with rates, and it really shows that there's a mass gap. There's at least a break. I'll not say a gap. It's not there yet. Okay. So to tell you whatever I have said so far are about individual events, right? So these are all individual events detected with an SNR above 12. That's not the only story. There's something more to it, and that's about the stochastic gravitational wave background. What is stochastic gravitational wave background? So this is my cartoon exam diagram trying to tell you in one picture. So let's say we are detecting gravitational wave sources from binaries, and this is my detector horizon. That means any sources up to here, I can detect with a SNR distant enough to call it an event. So if I see this event, I call it an event. And these sources, which may be coalescing at higher distance or redshift, we don't see them as an individual event, but their energy in the gravitational waves will show up in something called as the stochastic gravitational wave background, which we basically write as the integration over all sources which are contributing to your gravitational wave signal. They are distribution of masses, spin, and so on, and you integrate all sources. That means anything which contributes from here up to any higher shift you want to go, that will show up in the stochastic gravitational wave. The way to understand it, if I have more sources, stochastic gravitational wave background will be louder because rates goes up. If masses are heavier, signal goes up. So this is the quantity which usually people measure, which is nothing but the power spectrum of the stochastic gravitational wave background. Okay, so now I'm saying there are two probes. One is the individual event, which are detected by LIGO. Other is the stochastic gravitational wave background, for which you can measure the power spectrum, which you can write by this expression. What are our current constraints from the collaboration? So we have so far not detected any stochastic gravitational wave background. We have only an upper bound. This is the latest plot from the collaboration showing you the correlation, the omega GW as a function of frequency is, you can see, basically consistent with 0 with our current noise. Of course, things are going to change as our detector sensitivity is going to improve. So here comes the plot, which I was telling you will be interesting, and I'll bring it up. Is what I now, let's spend some time on this plot, this table, try to see where exactly primordial and astrophysical black holes are truly distinguishable, right? Whether primordial black holes are dark matter or not, that's a second question. But if I see a black hole of say 100 solar mass, I need to convince myself and then everybody else that this is really a primordial black hole. Okay. So let's take a simple approach. In the y-axis, I have put the redshifts from the arguments we have made so far, and the x-axis I have put the masses. So masses below 1 m sun is definitely not astrophysical origin mass. So if I detect those sources at low redshift, this is a right away I can say something that they are of primordial nature. Low mass black holes. If I detect low mass black holes at high redshift, above redshift 2, where my cosmic noon is present, that's also a promising window because, you know, very low mass objects you don't see as astrophysical origin. I mean, there is no solar model will do that for you. Then come the other range, which is between the mass is between some m mean, which you can take for your favorite choice. We don't have a priori choice. We currently in the collaboration take something around 5 solar mass, but we do not really know whether that's 5 is 2 or 3 or so on. And the MPISN value, which I was just introduced in my talk today. So if you see black holes in this mass range, this is a one which is quite polluted by astrophysical sources in comparison to primordial one. So if I see them in low redshift, if I detect a source, I cannot be sure whether it's of astrophysical origin or primordial origin, because I can have a significant contribution coming from the primordial astrophysical origin. But if I go to very high redshift, am I still sure? The answer is no. That's what you were mentioning. We do not understand the initial mass function very well. We do not understand the merger rate very well. So we have a significant amount of contamination even at high redshift for this range. The other place is go beyond MPISN, detect very heavy black holes. As soon as you see them, is that a clinching window to detect, say that it's a primordial black holes? Possibly no again, because you have so many astrophysical channels, uncertainties, and also there can be secondary black holes. Two black holes form a secondary, another black hole, and that may be merging another with another black hole. Those are like the secondary mergers. So again, at very low redshift, this is not very clean. But if you go to high redshift for above MPISN, you have a window. You cannot form stars. Before stars are formed, you cannot form heavy black holes and merge them significantly in number. So if I start seeing black holes at higher redshift in different mass windows, I possibly have a place to go for and argue that, okay, I have seen a black hole which is possibly of primordial in nature. And if you compare this with the plot I have shown you before, well, we are really, you can see this is what I can see sources. So this window, I cannot see as an individual event by any redshift. These are everything over here will contribute to stochastic gravitational background. So anything above this line, we can contribute to stochastic background for a particular detector. So very low mass end, you will detect from what? Stochastic gravitational background. Objects above MPISN at higher redshift, stochastic background. And even if you go to very high redshift, above stochastic background. For this discussion, I'm not focusing on these plots at all. I'll come back soon later on this. So now the question is, we have two windows, so as two ES part, I can now start observing through a new window available to us called the stochastic gravitational background measurements. I'll often call it SGWB in my talk. And I'll argue that stochastic background can provide a smoking gun signature for primordial black holes, just based on this mass redshift plane is features. Yeah. No, sure. That's right. That's right. We don't. So for individual event, to detect an event, we need a template. For stochastic gravitational background, there is no template search. It's a search of asking, do you see additional power between two detectors or not in comparison to your noise? Suppose you take two LIGO detectors.
You need more than one.
Yes, precisely. You need more than one. We have at least two working. We have also Virgo. Kagra is joining from this year. So we basically take all possible pairs of detectors and ask, do I have additional correlated signal or not? Noise will not correlate, signal will correlate, and that's the trick. Okay? Yeah, please. For gravitational waves. Yes, my suggestion to all my theoretical colleagues here, when you are calculating the stochastic gravitational background power spectrum and prediction, do not forget about something called as the overlap reduction function. To calculate the stochastic gravitational background signal correlated means I have a signal measured here. The same signal is correlated in this detector, means I should measure the signal in phase, right? That's what the different detectors orientation will be captured by something called as the overlap reduction function. Please take that into account because that really shrinks the window over which you can detect stochastic background. With a configuration like LIGO, two LIGO detectors, we cannot really go beyond around 60 hertz. So in all those plots, please multiply by the gamma square, which is available. And if you do not find it, please write to me. Okay, so yeah.
Can you go back to the yeah. So how do we what is the lowest mass of neutron star that can form?
We do not know it very well. We take it around, one solar mass and so on, but there is not there are a lot of uncertainties over there. So that's a bit hazy window. We current yeah, but a higher end, lower end. He's a lower end. That is a pain.
Lower end is where to measure primordial mass.
Yeah. But that's why this M mean, if I really go beyond 1 m-sun, which is compact enough, a compact object of very low mass will be a challenge for astrophysical objects to form. Compactification matters, right? Because see, in LIGO, we can really see two objects very, very nearby. So if they are not black holes, they will have tidal deformations. It's a different fact that tidal deformations currently are not detectable because our high frequencies are not really available to us. But when our high frequency modes are available and these two black holes are quite nearby, two compact objects are quite nearby, we can actually tell you about whether there is any tidal deformation on a object or not. And that will tell you about the equation of state or compactification. That's yes, yeah, that's right. Black holes. Yeah. So you typically take it around 1 m-sun, let's say, for searches. But again, this is not something written in stone. You can do analysis and show that there's not much support so far.
And LIGO at the moment cannot tell the difference between neutron star and black hole.
Right. That's because we do not measure tidal properties.
Neutron stars are all in the mass.
Correct. Our a priori assumption that there is a in this range objects, we'll call them neutron stars. That's right. Yes. So far, unless you do a multi-messenger search. How much time do I have? Only 5 minutes? Oh no. Can I add some discussion time on this? I have lots of slides to cover, by the way. So now if I put the, like the astrophysical and the primordial picture I told before in the one single observable, that is the merger rate. This is a plot as a function of redshift in the x-axis and merger rate in the y-axis. When primordial black holes are not present, you will track the stellar distribution for different scenarios. This is with the least amount of primordial black holes. As you keep on rising the primordial black hole fraction, you can basically see this enhanced distribution at high redshift. That's the key. Primordial black holes predicts as you go to higher and higher redshift, the merger rate of the black holes are going to be more in comparison to astrophysical black holes. One is the slope with negative slope, the merger rate will be decreasing as a function of redshift, other will be increasing. And that's the key window you'd like to explore. We really, as I say over here, there is a huge amount of uncertainty in this amplitude. There is something called more and more sophisticated calculations you do, you realize that there are several unknown parameters which can actually change the theoretical signal strength, which really kind of shadows our current understanding of primordial black hole constraints at the low redshift. But as you go to higher and higher redshift, you basically start seeing a significant difference in their merger rate, whether they're astrophysical or of primordial nature. Well, given that, is it sufficient to constrain astrophysical black holes and primordial black holes? And if someone is saying about primordial black holes are dark matter or not, that's secondary question. So what I am more interested now is, given that fact that I detect black holes, or I will detect stochastic aberration at background, what can I tell about the fraction of black holes in primordial nature in comparison to astrophysical black holes? What fraction of black holes? But for sure, we are seeing as coming from astrophysical or primordial origin in comparison to our current understanding of astrophysical black holes. So that's one of the observable probes we have, which we can go up to quite high redshift using stochastic background. So here is a plot of the stochastic gravitational wave background power spectrum, the one which I've shown you just some time back, showing you the spectrum in the y-axis, the function of frequency. PBHs are shown in dashed line, ABHs are shown in dotted lines. for two different sensitivities, LIGO 5 and A+. The main take-home message is black holes of masses which are above higher solar masses will tend to give you a slightly redder spectrum of the omega GW in comparison to the astrophysical signatures. The way to understand it is because if the black holes we observe are redshifted, their masses are redshifted, right? So at lower, if the black holes are emitting signal of certain mass, the corresponding maximum frequency up to which they can emit signal is lower. Maximum mass of emission is inversely proportional to the total mass. So if there are no black holes present at above a certain value in astrophysical searches, so that gives you a certain mass scale limit. Whereas if primordial black holes are really present up to very high redshift, then those will all start populating your lower end of the frequency because those are more redshifted. Simpler to understand this is like that. So you can basically get a redshifted gravitational wave stochastic background, which will be slightly redder, means more power at lower frequency than higher frequency. And I'm specifically plotting in this range to make sure, this is the bottleneck of what is called the arising because of the overlap reduction function. Otherwise, your every noise will look very clean and nice. So this is the only range which I have around 50-60 hertz up to which you can detect signal. So this is the spectrum which you would like to measure. So as I already told you, LIGO have so far not detected stochastic background, but the merger rates that at very high redshift there can be a lot of black holes of primordial origin can form and merge. That can itself be constrained from the current data of LIGO Virgo background. So this is the plot on the bound on the primordial black hole parameters from the LIGO Virgo data from O3. So this is the merger rate evolution denoted by alpha. This is the corresponding delay time for the astrophysical black holes. And this is the local merger rate. So the main take home message here, though we have not detected stochastic background, it really puts a cutoff on the merger rate evolution of the primordial black holes. They're currently very weak constraints. In future, this is going to be an extremely important probe. Here is a plot showing you the forecast for O5 and A+ of 4 parameters. One is FPBH over ABH, fraction of astrophysical primordial black holes over astrophysical black holes. For this forecast, we have taken it as 1. That's the black line over here. Mass of the primordial black hole. Heavier the mass, easier it is to detect. Delay time distribution of the astrophysical black holes. That's an uncertainty which you need to marginalize over. You can see the contours are quite non-Gaussian. And finally, the redshift evolution of the primordial black holes. The redshift evolution of the primordial black holes has a very clean prediction around redshift of alpha value of around 1.28, 1.3. We can see that we can right away, if there is an existence of primordial black holes, they will show up in such a high amount of stochastic gravitational wave background in comparison to astrophysical one, which we'll be able to measure. That means if we detect a loud stochastic gravitational wave background in the common detectors, which is slightly red in nature, that's a smoking gun signature of primordial black hole present at high redshift. What about the lower mass end? That's what he was asking about black holes below, say, 1 solar mass. So here is a plot. Again, in the y-axis, the merger rate, the x-axis, the redshifts. This is for the 3rd generation detectors. Remember, when I say stochastic background, you should right away ask someone what is the detector sensitivity you're talking about. What is stochastic for LIGO is not going to be stochastic for Cosmic Explorer and Einstein telescope. So here is a plot again of the astrophysical black holes merger rate in magenta, primordial black hole merger rate in blue, and in different dashed line is the horizon up to which you can see gravitational wave sources, say of 0.1 solar mass, 1 solar mass, and 3 solar mass. The way to understand this plot is as you go to higher and higher masses, the gravitational wave signal is louder. If they are louder, they will be easy to detect up to higher distance. So anything which is shaded like this will contribute to your stochastic background. Again, this is not in a very interesting astrophysical primordial background regime, maybe, because there can be sources of astrophysical origin in 3 solar mass. If you come to 1 solar mass, you can clearly see right just before 1 redshift of 2 and above, everything contributes to stochastic background. If you look for 0.1 solar mass objects, definitely of primordial origin, from our current understanding, anything below around 0.7, 0.8 will show up in the stochastic background. Okay. But the main contamination for 3rd generation detector for the stochastic gravitational background from primordial origin is going to be the neutron stars. They are the weaker ones. So they are the astrophysical contamination. So if you're going for a 0.1 solar mass or 1 solar mass objects, 1.4 solar mass ish neutron star can be a contamination. So that's your magenta line and saffron line. And in the over here, I am showing you the plot for the primordial black hole contamination. Please see the masses. They're very low mass, 1 solar mass and 0.05 solar mass. And this is the noise curve you can expect from Cosmic Explorer and NASCAR telescope on the stochastic background. That means stochastic gravitational background will be able to go to very low masses and tell you whether there is existence of them numerous in number at high redshift or not. Here is a plot. Because I'm a cosmologist, I have just learned to show contours and contours. I have to show a contour plot. This is our measurability on FPBH. There is a fraction of PBHs in low solar mass, in red and yellow for 1 solar mass objects, around 1 solar mass objects, and for violet and cyan for 0.05 solar mass objects. What is interesting here is that with 3rd generation detectors is really going to make a very neat difference in the measurability of the primordial black holes in this range. Again, through stochastic background. And the reason stochastic background is quite interesting is precisely because of a reason that the mass redshift plane, they can separate astrophysical black holes from primordial. No, these are values are taken at 1, but your error bar goes both sides. Our prior is basically flat. We have taken a flat prior. No. Yes, so we have taken a flat prior completely throughout. Yes. Otherwise, you basically get a distribution like this. TD min is the minimum delay time for the binary neutron stars to merge. Because see, the way to think about it, if the binary neutrons have a very little delay time, then they will be contaminating more towards redshift of 2 and above. And there can be a significant fraction of them at higher redshift over here because they are forming stars. So even a few of them will be showing up as a contamination to the background, and that will show up to your level of this level of signature.
Stars can form at different times.
Yes.
Then thereafter, the TD is the time.
Yes. So see, objects forming individually, then they form a corresponding compact object. Then they need to find a time to coalescence. So the time to coalescence is what we measure this in gravitational wave, and our time delay is from star formation till now, till that time. And this depends upon different formation journeys. That's another physics which you want to explain. Right. So people are doing simulations now that if these primordial black holes are really forming in an extremely higher density regions, they're likely to be very clustered. So that means those objects are basically forming in the region where all of them are very nearby, clustered. So they will quickly merge to them with a very short amount of delay time, and most of them will be emitting signal at a very high redshift than at low redshift. That's precisely one of the reasons why you may see low amount of primordial black holes merging at low redshift, because they may be mostly merging at higher redshift because of clustering. Yes.
if you have high overdensity region of PBHs, then suppose two PBHs are trying to form a binary, but others will interrupt that binary formation, right? So it will
So it
reduce
will
the merger
depend.
rate.
Yeah, it will soon turn out to be like a three-body problem,
Yes.
and so on. But you will still have a significant fraction of binaries which will coalesce. So you will your eccentricity of the orbits will be different. Your spins will be a bit different, but you can still merge them within your observable time of the age of the universe.
No, I was thinking that if they don't merge, even if they don't merge, but you will have a higher quadruple moment,
Yes.
will generate a huge amount of gravitational wave signal that can be detected.
Yeah, that can also be detected. Okay. Yeah, sure. So you are saying that even they are not merging, but they are just, yeah, sure, of course. So here we are talking mainly about sources which are either in the inspiral state, that's the one which you're talking about, or maybe merging. They need not be merging at all, right? I'm basically just caring about what fraction of these objects are in the inspiral stage at a particular frequency.
What did you assume for that?
So that fraction is basically coming from your merger rate, right? We play with a free parameter, and that's the fraction you play with. You change that parameter as a function of redshift.
Get this Dutta.
Yes.
What did you assume?
So here your FPVH fraction is assumed to be same as the local merger rate, and you extrapolate that from LIGO. Yeah, from LIGO, we have a measurement of around 20 per gigaparsec cube per year. So that's the number which is going over here.
That's of all black.
All black holes, yes. So that's the only number we have right now. So here in this plot, I have taken the local merger rate to be same. So these will scale up and down depending upon your different models. And these redshift evolution will be around 1.3-ish. And this you can probe.
That whole thing might be far below detectability, even if
No, so you have a limit to that. You can show that this factor can be from simulations are kind of about factor of 1,000. The suppression factor of something around 0.1-ish to around 1,000. 1 part in 1,000.
what environment are these?
So these are dense systems where you have extremely high curvatures or non-Gaussian situations. These black holes can merge very fast.
Is there a cosmological simulation?
No. I must confess here that the people who are working on the primordial black hole setups, there are many more work to be done in really doing sophisticated cosmological simulations and exploring this setup. These are still quite new sector. It's really, I would say, more data-driven than theory-driven so far. But you can always make this measurement of is there any component of black holes which has a merger rate with rising distribution than like the falling tail. And even if it is a significantly less fraction, it will show up in your tail because this very fast goes down. This goes down very fast. And you can clearly see at redshift 7 is a huge difference. And this keeps on growing. And you integrate everything in stochastic background. Stochastic background is anything, say, for 0.1 solar mass from here to basically infinity. I think I'm really lacking. I should just finish. Yeah, sorry. So can I just take 5 more minutes? Well, okay, sorry. So the final question now is, so far I have only told you about power spectrum. So is power spectrum a sufficient statistics? So power spectrum is great when a distribution is Gaussian, as you all know. Possibly that's not the case. This is I'm trying to show a simple scenario where, let's say in blue you have noise and in orange you have signals. This signal is very, very non-Gaussian or time dependent. And there are 2 time scales which are involved in gravitational wave signal, which you are detecting in LIGO. One time scale is time scale over which the signal appears, means this time scale. Okay? Driven by the merger rate. The second time scale is a time scale over which the signal is present. This. And that time scale is driven by the chirp mass time scale. And you can show that this stochastic gravitational wave background will end up being a completely non-Gaussian distribution. So whatever I was showing so far about the power spectrum of the stochastic gravitational wave background is no way the sufficient statistics. And that's what one of my students, Mohit Ratshah, is the plots, all plots made by him, has been showing that the simulation he has made for the stochastic gravitational wave background for astrophysical origins. As you can see, he has changed the pair distributed supernova masses and has shown that there is going to be a significant amount of non-Gaussian distribution of a signature. Presence of non-Gaussian signature opens up a completely new window for you to explore stochastic background. That means you have much more information in higher order statistics. Story is quite similar when you are looking at the primordial black holes. This is a simulation run by him or for primordial black holes. Again, you can clearly see the distribution of omega GW is again very non-Gaussian depending upon different setups of astrophysical black holes and primordial black holes of different masses. It's still a work in progress. And you can clearly see that maybe our next step for us to really go for is there is a new theoretical signal in the higher order statistics of the stochastic background, which we should measure from data. There is until date no effort made in measuring non-Gaussian stochastic background. We do not know what exists in data so far. That's what we are working currently. Finally, this stochastic gravitational wave background will have an intrinsic fluctuation. So this is omega GW average. That's the number I was showing so far. But this signal will have a fluctuation with a tail. The way to understand this plot is heavier the black holes are, more non-Gaussian the distribution is. So you would like to look for if there is primordial black holes of above PRS distributed supernova masses, we will be having a tail in the omega GW distribution, which is detectable from future detectors. So I think I'll end here with the simple take-home message that if you want to really go and say the primordial nature of primordial black holes, what I will say is peering into the high redshift through stochastic gravitational wave background can actually give us a smoking gun signature for PBHs. So that's the range you should go for. And of course, there is many multi-messenger signatures which one can explore. And this domain of multi-band observations and we can really tell us a huge amount of astrophysical and fundamental physics quantities with the help of these several detectors which are lined up. With this, I will end my talk telling you that gravitational resources are the new probes through the high redshift universe. These are really like we used to do with quasars, we used to do with Lyman alpha. Now we have another new probe like gravitational resources. Stochastic background will be an intrinsically time dependent or non-Gaussian, and that's so Gaussian is only half of the story. There's a significant half remaining which you need to explore. And with stochastic gravitational background can show the existence of primordial black holes from LIGO, Virgo, Kagra, and in future from Cosmic Explorer and Einstein Telescope for different mass ranges, as I have shown, which will be really a smoking gun signature for us if we're able to detect it. Thank you so much. I'm sorry for taking a lot of time.
Okay, so yeah, we have had a lot of discussions during the talk, but maybe we can take a couple of quick questions now.
So I believe there are uncertainties in the mass function of the initial mass function of PBHs also. So do those affect these conclusions in any way?
Initial mass function of PBHs are completely unknown, and that's the thing we are going to measure. So there is no initial mass function. Like for stars, we talk about the initial mass function of stars. Here we start with the initial mass function of black holes. We want to start measuring that initial mass function of black holes precisely. So in these particular plots, we have taken log normal distributions of the PBHs, but you can take different mass ranges. The sensitivity of varying the distribution will not show up much. What really shows up is in which mass ranges do you have more number of black holes. That will end up showing in this plot. So what you have to understand is whichever is more in number will be the more significant contribution to the stochastic gravitational background. And the signature you should look for, that mass will typically drive the shape of the omega GW. And more heavier that is, more redder the spectrum will be. That's the signature you should look for. But we need to marginalize over those different models as well if we see something really showing up in the background.
Hi. First of all, nice talk. It was quite enlightening. So in the sky map that you are showing for manuscript in preparation. Yeah. So here we can see these diamonds like diamond-like structure. They are just heel pixels. So what is the inside of the?
So this is done with inside 128, if I'm not wrong, or 64. I do not exactly remember. These are taken in the way so that your angular resolution of the two detectors matches with the typical resolution.
CMB scales.
No. So you have a resolution from two detectors. You take that and you match that with the angular resolution you get in these maps. So npix inside gives you the number of pixels. Total number of sky, 4 pi divided by number of pixels will give you the square root of that, will give you the total number of area, and that we compare.
Okay, so it's either 64 or 1.
Yeah, right. And these are simulations which he has made. Basically, he has written a code which can take an astrophysical population, a primordial black hole population, evolve them as a function of over different time scales for the signal, integrate out everything from low redshift to high redshift, and then these maps are produced.
Thank you.
He has also maps for how the signal will look for at different frequencies, like 20, 25, 30 hertz, and this nicely shows our chirping wave.
Okay, I think let's break for coffee now. And yeah, we will see if we can get some more time. 12:10, we will come back for the next session. And yeah, we'll see if we get some. Absolutely, yes.
Okay, thank you.
Yeah, let's thank both the speakers in the morning.